and we'll pick up the slideshow at the current slide, though we have a little bit to do before we get there. All right, first, let me say this, because this is coming up soon. Just found out about this. Have either of you seen Hidden Figures? You have, okay? Have you? What did you think? Amazing movie, amazing story. Okay, the movie was good too, but the story.
True story, right?
Yeah, amazing true story. It's going to be at the Hill University Center. That's the Alumni Theater, and it's a new building there, so I can't tell you exactly where it'll be in there. Wednesday evening, March the 8th at 5 o'clock. So I don't know if either of you can do that, but this is for people at home too. If you can be there, it's worth it. Now, the worst thing about going to UAB is finding parking. Okay, there may be transportation leaving from one of the two campuses, either this campus or Birmingham campus, to take students. That I just found out about today, so I haven't been able to investigate transportation issues. Huh?
Is it free?
As far as I know, it's free. Yes. Yeah. And it's a great movie. So I've seen it too, and I want to see it again. I don't know if I'll be able to, but I want to see it again. And that's this Wednesday. It's a story of, I won't give too much away, but if you think about it, our earliest space efforts were made before computers were around. So they literally did it with human, and they named them computers. I didn't know that the people were named computers. They were called the computers, those people who computed the trajectories, all the things that they had to. And it's a story of 3 women that participated in that, and they happen to all be black women, and it's an incredible story, and based on a true story. And in fact, I think they're going to have some cast members there. That's what I heard. The guy who was telling me this read that. I don't know if they're major cast members. What's that?
Where I live close to the UAB. I can walk in front of the UAB.
Oh, really? Fantastic.
But unfortunately, I can't go there. I have a class 5:30.
All right. Oh, yeah, that's right. Yeah, your physics class.
No, after physics, I have PE class.
Oh, I see. Okay. Yeah. So anyway, spread the word around. You know, I think we've been included on it. The email came. I haven't seen it, but the studio was telling me the email came to us. So incredible opportunity. Okay. If there is a cost, it should be nominal, but he didn't say anything about a cost. And like I said, I haven't seen the email. Okay, that's one. Another. This is the beginning of the second mini-term. Okay, which means, and this is preaching to the choir here, but I'm talking more to people at home. On the academic calendar, they list that we're to submit midterm progress reports this week, Monday through Friday of this week. Now, both of you, I've gotten your papers and your first test. Fantastic. You've done everything up till now. One person in the class has turned in the first test with no paper, and another person in the class hasn't turned in anything. So the point being that if I need some sort of input this week, now here's the other thing. This is the disclaimer here. A lot of times they forget to open this for us to do. So if they don't open it, it's don't ask, don't tell. I don't bother to tell them, hey, you haven't opened this yet. You know, so what I'm getting at is, if they do open it, I have to put in midterm progress report, and that would mean a D or an F at midterm is all I put in. If you got A's, B's, or C's, not that they don't care, but they're trying to get the people who are struggling at midterm. So if I don't have anything, that's going to have to go in as an F at midterm. Not that that's going to harm you or tarnish you in any way, but you may be called and contacted and asked to get in touch with someone to see about tutoring or counseling or something like that. So to avoid the hassle, get something into me this week, okay, by Friday. All right, The other change that's happening, because this is past midterm, my first mini-term course ended last Thursday. I've got to get the grades in this afternoon or bust, okay? The second mini-term course starts tomorrow. The trouble is my hours are different. The hours for the class are different. So that does affect my office hours, but it affects them positively as far as y'all are concerned. It used to be on Tuesday, Thursday. What is it? Oh, okay. Okay. Oh, I thought you read about hidden figures or something. Okay. On Tuesday and Thursday, my office hours were 10:45 until 12:30. That was not bad. Beginning tomorrow, they'll be 10:45 till 1:15. So I actually have 45 more minutes of office hours Tuesday and Thursday. Of course, that means I'm also here 45 minutes later. I'll be here at least till 5:45 every Tuesday and Thursday. Probably closer to 6 o'clock. So, but I'll be in class most of that time. So I did want to let you know, change of office hours for the second mini-term. All right. Any questions before we get started on today's? Okay. My memory and mark in the book has us on chapter 12, section 12.3, example 2, right in the middle of page 646, okay, or near the middle of the page, okay, and this is the figure for it, I think, okay. Find the angle theta between V, which is 3, 6, 2, so here we come, tortoise on the x-axis 3 units, sort of to the right, but tortoise on the y-axis 6 units, and up 2 units from there, there's your angle V. Now, the angle W is 4, 2, 4. So coming tortoise to the left on the x-axis 4 units, to the right on the y-axis and tortoise 2 units, and then up another 4 units, there's vector W. Find the angle theta in between those two vectors. Now this is out there in 3 space. It's not a particularly trivial thing to do geometrically. Okay? Because if you imagine it, picture that, you're at some angle over here, the plane is going like this down through the origin, how to get that orientation and that angle. It's not an easy thing. However, the last thing we did last time was this. Theta, the angle between any two vectors in any space, is defined this way. The inverse cosine, and this came from, and from this earlier, cosine theta is the dot product V dot W divided by the magnitude of V times the magnitude of W. Take the inverse cosine on both sides of that, and that gives you this formula here. So, what do we do first? Let's go back to our figure here. What would we? 3 fairly simple calculations to make. What are they? You need to see the formula again. Second. Magnitude of V, magnitude of W, and the dot product between V and W. That's it, folks. All to do. Now, with this being our V and that being our W, how do we find those 3 things? In whichever order you want to do them. Second. Magnitude of V first, we can do that. What would that be? Square root of 9 plus 36 plus 4. That would be the square root of, which is 7. Always the positive square root, principal square root. Next, square root of 16 plus 4 plus, which is another 16, and that would be square root of 36, which is 6. Anything else? Dot product of v dot w, which by the way would be the same as w dot v, but doesn't matter. What would that be? 3 what? 3 times 4 plus 6 times 2 plus 2 times 4. That would be 12 plus 12 plus 8. That would be, second, 32. Okay. 24 and 8 is 32. Okay? So, you tell me. Marcus is here. All right. Marcus, something new that I found out since this morning. Have you heard of the movie Hidden Figures? Have you seen it yet? Would you like to? And you may have class in, I don't know. But it's going to be presented at UAB, the Hill Student Center, in the Alumni Theater of the Student Center, day after tomorrow, Wednesday, March the 8th, 5 in the evening. Okay? And from what I thought I understood the guy saying, they may actually have some cast members there for discussion afterwards. I don't know. You know the story, sort of? Okay. Incredible story. It's based on a true story. One of the ladies is still living. She was at the Academy Awards. I know Hidden Figures won some Academy Awards. I don't remember how many, but I know they did win. It's quite a movie. Okay? Now, I don't know if there's going to be transportation or not. I just found out about it the last period, so I don't know if there's transportation or not. Normally, I would be driving, but since I live so close to UAB, I'm going to drive there and drive home. I'm not driving transportation back, but we might be able to get someone to provide transportation. I don't know that for a fact. I do know parking is somewhat of a premium at UAB. So, but usually this time in the evening, hopefully they're not giving tickets any longer. But there are some streets off UAB that you can park not too far from the theater. Do all of you know where the Hill University Center is? UAB? You know how to get to UAB? Okay. You know UAB is on University Boulevard or Avenue or whatever. Okay. Name something on UAB campus that you're familiar with as a reference point.
Isn't the right in front of the visual art building, the UAB? They have visual
Okay.
performing art.
Okay. I don't know exactly where that is, but this is a new building that was just built. It's the corner of University Boulevard, and I can't think of the number of the cross street. But yeah, do you know Campus Recreation? Yes, it's right basically across the street from there. That new building there. That new building, yes.
Oh, okay, I know.
Yeah. Do you have any idea what we're talking about now? Okay. Glass building, really pretty building. Yeah, they have a food court there. Yeah. So you can buy supper there if you want to too. Okay. It's quite a nice. I haven't been in the new building. I could have told you where it was in the old building, but they tore that down and built the new one. So anyway, if you can get there. It seems like a lot of 6th Avenue And by the way, University Boulevard or Avenue is basically 8th Avenue in place of 8th Avenue. I don't know about 7th. There is some parking on that maybe, but I know 6th and 5th have a lot of street parking there. And I think you can park anywhere there and not have to pay or get ticketed, okay? So anyway, I wanted to let you know that. All right, let's go on. We were doing example 2 on page 646, chapter 12, section 12.3. Find the angle theta between these two vectors. Okay, we had just calculated what the magnitude of V was, the magnitude of W, and the dot product of V dot W. Okay? And then our formula from just above that example is theta is equal to the inverse cosine of the dot product, which was 32, divided by the product of V, magnitude of V times the magnitude of W, which is 7 times 6. So that's 32 over 42, which is 16 over 21, which I didn't have to do that, but it just makes it easier. What is that product, that quotient? 16 divided by 21? Pretty close to 0.75 or so, right? Anyone got it? A lot of telephones, I'm not sure if they have inverse cosines on them or not, but calculators do. And if you're stay in radian mode, probably the safest place to stay is what? Anyone got it? Inverse cosine of 16 over 21. 0.705, is that what you said? 7045. Okay. Approximately in radians, 0.7045. And in the book, they rounded that to 0.705. So that sounds reasonable. Okay? Now, any questions on that? Really makes finding the angles between two vectors pretty easy using the dot product. To do that geometrically would have been awful, okay? Or worse, okay? Now, next topic. Basically based on the same thing, since the cosine of theta is equal to that particular relationship, okay? Now, what if that theta had been 90 degrees perpendicular? What's cosine of theta of 90 or pi halves? Second? 0. So here we have that two vectors, V and W, are perpendicular to each other if and only if the dot product is 0. Because that's going to make the cosine of theta equal 0. That means theta has to be a half pi. Okay. Pi halves, negative pi halves, 3 halves pi, whatever. Okay. So, now, a couple of different names here. The terms orthogonal and perpendicular are synonymous and used interchangeably, although we usually use the word orthogonal when we talk about vectors. Lines we usually say perpendicular, vectors orthogonal. No real reason for that, but it is fairly common, okay? So two non-zero vectors. Now remember, that's the other thing. V and W can't be the zero vector, either one of them, because the dot product of the zero vector with any vector is going to be 0. So that would make the zero vector perpendicular to any vector, which really doesn't make any sense. Zero vector has no dimension. Okay, so these are non-zero vectors. We can use the dot product test to see if they're orthogonal for a piece of cake. The standard, in free space, these are our standard basis vectors. Okay, now, in this course, we haven't talked anything about basis. In linear algebra, we'll be talking about bases in the future, pretty soon, in fact. Okay, but the standard basis vectors for your three-dimensional coordinates, I, J, and K, are mutually orthogonal. And the other thing is they're unit vectors, so they all have unit 1. 1 unit here, 1 unit there, 1 unit there. Those are your standard basis vectors, and they are orthogonal to each other. Okay? And you can see that by writing them in their, well, this isn't, writing them in their component form. The unit vector I is 1, 0, 0. The unit vector J is 0, 1, 0. And the unit vector K is 0, 0, 1. 1 unit out in the x-axis, nothing on y, and z for I. J is 1 unit out on y with 0 on x or z, and k vector is 1 unit up on z with nothing on x or y. And if you did a dot product between these two, that would be 0 plus 0 plus 0. Between I and k would be 0 plus 0 plus 0. Between j and k, 0 plus 0 plus 0. Yeah, dot product is 0 between those three vectors, any combination of those three vectors, and of course, that would make them have to be perpendicular. Now, not only that, what if we dotted these with themselves, like I dot I? What would that be? Anyone do that quickly? Second? So that's that? No. It's the magnitude of I squared. You're absolutely right. And 1 times 1 is? Plus 0. So that would be 1. And certainly the magnitude squared of a unit vector is 1, because 1 squared is 1. Same thing here, j dot j. That magnitude is also, that dot product is 1, and k dot k, that dot product. I should have the other vectors in here, 0, 0, 1. I didn't do it for j. That's equal to 1 as well. Okay, good deal. Okay. But any other two dots with two dissimilar unit vectors, standard basis vectors would be 0. All right, I think we're ready for example 3. I think this is it. Okay, let's blow it up and see if we can see it a little better, and then we'll start fiddling with it. This is for example 3. Determine whether V, which is a 261, which that looks to be about right, come out the x-axis 2, down the y-axis, up the y-axis 6, and up 1 on z. U, which is 2, negative 1, 1, come out 2 on x, negative 1 on y, up 1 on z. There's your u vector. The w vector, minus 4 on x, positive 1 on y, and then up 4 on up 2 on j. Boy, maybe this is dimensionally correct, but it sure seems like that's a whole lot too long there for that to be Again, it's really, really difficult to represent 3 dimensions on a 2-dimensional board. Basically, almost impossible. You can come close, but boy, it's so hard to indicate. So, do you think you can trust your eyes on this? Think you can say, well, that kind of looks like it could be a right angle, or this sort of looks like it could be a right angle. Anyone want to trust this? Not me. Okay, smart move. Okay. How could we tell if these are orthogonal or not? Determine whether V is orthogonal to U or to W. How would you do it? Yeah, let's just do the dot product. Okay, we'll have to shrink back again. This V, by the way, was 261. Whoops. Okay. The U was 2, -1, 1. And W over here was -4, 1, 2. Okay? Is V orthogonal to either of those? Or both of those? I think even the picture would indicate it can't be orthogonal to U. But let's not trust it. What would be our test there? What would be our test? V dot U. And what would that give us? 4, -6, plus 1. Guess what? Not orthogonal, but it sure looks a lot closer than I ever would have thought. So, okay, that adds up to -1. Okay? How about V dot W? What would that be? -8. Wait. I can't believe I did that. I'll put a vector symbol in and it won't erase. Okay. All right. -8 plus 6 plus 2. Guess what that adds to? 0. Ding, 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 ding. These have to be orthogonal. And since we're here, you want to try U dot W? Just to see what that might be. What would that be? -8 -1. Yeah, plus 2. Nowhere close. Okay? Now, I can't believe that the first one's closer to 0 than the last one. I don't know if that really means anything. They definitely are not orthogonal. Okay? Either one of them cares. But U and V and W are. Okay, let's go to example 4. I don't think there's a picture here. No, there's not. So let's use the same slide here to do example 4. Testing for obtuseness. What in the world is obtuseness? Any of you see the Shawshank Redemption? It's an old movie. Nowadays, it was fairly new when I was young, but a really good movie. If you ever want to check one out, it's a really good movie. What's that? Yes, you got it. You seen it? Yeah, good movie. Shawshank Redemption. Okay, the hero in the movie, I guess the protagonist, who was imprisoned falsely and kept in prison and treated really badly by the guards and used by the warden and all this kind of stuff. Something was said at some time or another, and he was working for the warden's son because he was an accountant and very good with numbers, and he began helping some of the various people there, the cards and the warden, with their taxes and with issues and various things. So they had him set up to do things, and the warden was talking to him about something, and he called the warden obtuse. Why are you being so obtuse about this? He got put in solitary for like a month or something like that. So whenever I hear the word obtuse, I think of Shawshank Redemption. That's not what we're talking about here, okay? What do we mean with obtuseness in terms of vectors? What do you think those mean? What about it? Okay, and what do you mean by obtuse angle? It's what?
It's not an acute or a writing.
Okay, and what does acute angle mean?
Less than 90.
Less than 90. Right angle is 90. Obtuse means generally between 90 and 180. Okay, or pi halves and pi. Though I guess technically any other angle would be obtuse too if it's just greater than 90. But most of the time we refer to it as being in the first or second quadrant. Between the first and second quadrant. In the second quadrant. Well, let's put it that way. Okay. Between 90 and 180. Okay. But it could be anything. Determine whether the angles between vectors v, which are 3, 1, negative 2. This is not this vector. 3, 1, negative 2. He's not this one. Okay. And vector u, which would be, I've lost my place now, 1/2, 1/2, 5. Okay? And w. Vector w is 4, negative 3, 0. All right. Now let's back up a moment and let's go back to what Emmanuel was saying. He said an obtuse angle is not acute. Now what do we know about acute angles? Oh, that's acute, not that. What do we mean by an acute angle? What do we know about it? Less than 90, for sure. How about its trig functions? Any idea? 36 to 90. Okay, that's 30 and 60 are acute angles, that's true. But what about, okay, in which quadrant do acute angles live? Yeah. First quadrant, right? Between 0 and 90, that's in the first quadrant, right? Okay, and what can you tell me about all those trig functions? They're positive. All the angles are positive in the first quadrant, including the cosine, right? Okay? Okay? Including the cosine. Now, put this back up. Actually, we could go back a few more. Yeah. I'll even blow it up for you again. Okay, focus on this right here. Cosine of theta is the dot product of v dot w divided by magnitude of v and magnitude times magnitude of w. What can you tell me about the magnitude of v? Always positive, because we assume these are non-negative angles, two non-zero angles, two non-zero vectors. So that's always positive. This, always positive. And if theta is an acute angle, cosine is positive. So what does that tell you about the dot product? Positive. Okay. So we just have confirmed or shown that if the dot product of two vectors is positive, if the two vectors are in the first quadrant, well, if they're, that means they're between 0 and pi halves. Okay. Not quite. Where else is the cosine positive? Fourth quadrant. So that means if the angle between the two vectors is acute, whether you measure it this way or that way, clockwise or counterclockwise, if it's acute, and that's all we're going to deal with. We're not going to deal with anything past 180. Okay, we're going to deal with this. So if it's in the first quadrant or fourth quadrant, then it's got to be acute. Okay, that will be positive. And obtuse was not acute, but not 90. What if these were right angles or pi halves? What's the dot product? 0. Okay, so it's not going to be positive. It's not going to be 0. Guess what it's going to be? Negative. And remember when we did this? And nope, not that one. This one. No, it wasn't that one either. Okay, I guess I'll erase it. When we did that other one, the one that we did from here, and we evaluated these, one of those came out with -1.
It was B times W.
Yeah. V dot U was -1. That means obtuse. Sure enough, that is obtuse. Okay? And in fact, remember I said it's sort of funny looking, sort of straight, but you see, an angle with itself, what's this dot product? It's magnitude squared. No. Perpendicular is 0. This way, maximum. So maximum, 0, and it's approaching maximum again. Well, this would be, if these were unit vectors, that would be 1. V dot V would be its magnitude squared. Okay? So V dot U, for that to be negative, that's, anyway, negative would mean obtuse. And then we did V dot W, found out that was 0, so that was, and then we did W dot U. What did we find out about that? I think it was also negative, wasn't it? Yeah. So that's also obtuse. It doesn't look like it here, but it was. Okay? So I think we've got basically what we need. Determine whether the angles between these two vectors, vector V and U or V and W, are obtuse. So what have we got to do that? Do a dot product. And between these two, what's the dot product? V and W. Which is 3/2 plus 1/2 which is -10. These two add to 2 minus 10. This will be -8. I would say those two are definitely obtuse, right? And then the next one, that's a U. Here's V dot W. What would be the dot product of those two? Which is 12 plus or minus 3 that last would be 0, right? And this would be 9. So what can you tell me about those two? Acute, because it comes out positive. 0 if it's perpendicular or orthogonal, negative if it's obtuse. Okay? So, and the angle between V and U, obtuse. Angle between V and W, acute. All right, good deal. Let's move on to example 5. Okay, now before we do that, here's the generalization, which we just used, which we could have done before we did those problems too. The angle theta between any two vectors V and U is obtuse if the dot product is less than 0. What they didn't say here, but it's acute if it's, is greater than 0 and perpendicular if, or orthogonal if it's equal to 0. Okay? Got it? All right. Now, let's do example 5. I don't think we have a figure for that either. So, let's do it here. Find the vector orthogonal to W. I think we're going to call this vector V, which is orthogonal to W, and W is named to be 1, 3, 2. Okay? That's all they say. Find a vector V which is orthogonal to W. What they suggest, and it's the way to go here, is to name this vector V. It's in 3 dimensions because otherwise it wouldn't make any sense. So, come up with some coordinates for V. Hint, not numeric. Make up some coordinates for V. Say again? X, Y, Z? That would work. They use ABC. I don't know why. Okay? But anyway, what if that's V? There's W. How could you find out, make V to be orthogonal to W? Okay, yeah. Dot product them together, and that would be X plus 3Y plus 2Z has to be 0. Okay? Now, leaves you a lot of possibilities, doesn't it? There's an infinite number of vectors V perpendicular to W. It just says find a vector orthogonal to that. Do any come to mind right off the top? What if you let Y be, say, 1? What could your X and Z be to guarantee that's going to add to be 0? How about -1, -1? Would that work? There's a vector orthogonal to W. Let's see if it works. -1 plus 3 minus 2. Sure enough, that works. Right? Certainly the 0 vector will work, but we're talking about non-zero vectors, so stay away from 0 vectors if you possibly can. They're bad news, okay? But there's an infinite number of them, and I think they're all multiples of that, so you can pick out any multiple of that you wanted, okay? They used ABC. What they did, they started off with AB1 and BB1. Okay, that's one way to go, or XB1, YB1. So that'd be 1 plus 3 is 4, so you need Z to be -2. That works, yeah, perfectly fine. So all of them aren't multiples of it. Certainly every multiple of that would work too, but there's a bunch of them that wouldn't be multiples. In other words, if these are orthogonal to each other, that's also orthogonal, and that one, and that one, and that one, because this is a right angle always between here. So they don't have to be parallel to each other. Good deal. Infinite number. All right, now the next part. The projection of one vector along another vector, that's what we're dealing with. So here we have a vector u, and we want a component of u, or projection of u, parallel to v. Okay? The projection of u along v would have this length. Okay? Now, I can't recall if we've used this symbology before. They're acting like we have. But in case you don't recall it, and I can't remember, I've used it lots, so I don't know, I can't remember in this book. The component, okay, this vector u in relation to that vector v has one component parallel to v, and I'm going to have to shrink this to draw what I want to. This component of u would be called the perpendicular component. Okay? So you've broken this vector u into one component parallel to u and another component perpendicular to u. If you had u parallel to u perpendicular, you sure enough get u. Okay. And parallel means it's parallel to v. Now, what would be the magnitude of this vector, u parallel? Well, since we know that the cosine of this angle theta is equal to u parallel, that magnitude, divided by adjacent over hypotenuse, the magnitude of u, then, let's write that down, the cosine of the angle theta between those two vectors, this is getting uglier all the time, is equal to the adjacent side, u parallel, divided by u, and make these magnitudes, okay? So u parallel is probably, no, I guess they draw it as a vector. That is the cosine of the angle, the adjacent side over the hypotenuse, okay? So let's take this, and then u parallel, the projection u parallel, I'm going to write it like this. It has a length, I hate writing it this way, absolute value, multiply both sides by magnitude of u times the cosine of theta, and you get what the magnitude or length of u parallel is. Does that make sense? Okay. Now, just a couple of points here. They've drawn in another little e vector here with a v as a subscript. What does that mean? Unit vector in the direction of v. So since u parallel is defined to be in the direction of v, it's also in the direction of the unit vector in the direction of v. And if this is greater than 1 here, then u parallel is some multiple of EV. In this case, it looks pretty close to 2 EV, but that's hard to take for sure. And yeah, we usually don't mess with u perpendicular that way. So I can't think of anything else to do with that. That's called the projection of u parallel to v, or u parallel. Okay. Now, we've said what it is, But how is that related to a dot product? This whole section is on dot products. Why did this suddenly show up? Okay. Well, if you think about what a dot product is, the dot product of U and V, give me one definition of that. There's several. Dealing with absolute values. Okay. Let's go back a little ways. Right here. V dot W is the magnitude of V times the magnitude of W times the cosine of the angle in between, right? Right there. That's one definition of dot product, okay? So let's go over here. All right, U dot V would be, tell me, magnitude of U, magnitude of V times cosine of the angle in between. Well, if we just were to divide this with magnitude of V, we would have exactly what we have here. And that is U parallel. Okay? And they call this U, have strange notation, U parallel to V. Okay? And they do bold that, so that would, let me put my hat back on it. I didn't want to be too confusing with it before, but it is indeed true. So here we have a definition. Now, it doesn't quite look like what we have here. In fact, the third part of equation 4 does, except this is all scalar. U dot V is scalar, magnitude of V is scalar, and we want this to be a vector. Okay? Okay? Hope I made the same. Yeah, that's basically how they wrote it. Okay? This is a vector. This is a scalar. We need something else in here. What you reckon that is? That's just a magnitude. That E sub V. Actually, that's a unit vector. You see, E is a unit vector. Basically, what unit vectors do is give you direction. That's the direction of V. This is the projection of U onto V, so that's got to be in the same direction of V. All we have to do is add the unit vector, multiply this scalar number by that unit vector, and this gives you that. Sure enough, that's what they have here. So that's the third side of the equation, maybe fourth. Let's get what some of those other things are. See if you remember this one. What is magnitude of V? Or more precisely, magnitude of V squared. Remember what that is? V dot V. V dot V. Absolutely. That's magnitude of V squared. Okay. So if instead of magnitude of V, we put, all right, one more little step here. This E to the V, what's another way of expressing that? The unit vector in the direction of V. See if I can find it. Maybe the previous slide. Yeah, it was the previous section. Not in this one, but it was in the previous section. Second. Okay, it's V, it's got to be a vector, divided by its own magnitude. Right? That'll be the unit vector in the direction of V. Okay? So instead of this then, we're going to put V times dot V. So we'll put this as being U dot V over V magnitude of V times magnitude of V, which is V dot V times V. Okay? It's strange seeming, but it's indeed true that U dot V divided by V dot V, that's what U dot V is up there, V dot V dot V is here. Here's V dot V times the V dot V over here, that would give you your E sub V. So these two things give you V dot V, and this is just direction here. Because you see, this is in some direction. So this is what the projection of U onto V would be, U dot V divided by V dot V, all multiplied by the vector V. That gives it a direction. Okay? So there's the first equality in that group of three. And instead of V dot V, we could write this. So the second would be U dot V over the magnitude of V squared times, times V. That's it. Okay. All we did is substitute V dot V to be magnitude of V squared. So there we've got all three sides of this equation. Well, no, it isn't. The old edition of the book gave the ones I just gave. The new edition of the book, the current one we're using, no, it isn't. No, this is the old edition of the book. Gave this rendition. The new edition for the projection writes it like this. U parallel to vector V, okay? The ones I just did, U dot V over V dot V times U, okay? I'm sorry, V, goodness gracious, I'm stuck on U. Stuck on U, no. V, okay, in the direction of V. U in the direction of V. Second rendition of that is U dot V over, because V dot V is magnitude of V squared, and that's times V, okay? And the other rendition of this would be U dot V over V, just magnitude of V. Pull one of those out and put it under the V, and that would be E dot V, sub V. Okay. So those are the three renditions of this. I like them a lot better than the previous edition. This is certainly still true. But U parallel to V would be the dot product of U dot the unit vector in the direction of V times the unit vector in the direction of V. Well, we see this one's true if we put one of these magnitude of V under this one and the other under this one, then this would be U dot EV times EV, okay? Or, and this one is exactly like that, okay? So these two are the same. This is a lot like this. If you take one of these magnitude of V and put it under this one and that one, that is U dot E sub V times E sub V, okay? You really don't have too much that looks like the third one, but that's okay too. Now, I think this is the figure that goes with that. I don't know why, but about the middle of the last class, my head just started closing in on me. I don't know if it's something to do with the ventilation here or what. Now, this is basically from those last equations we have. If this angle is obtuse, meaning greater than 90 but less than 180, greater than pi half, less than pi, if that angle is obtuse, then the projection of U in the direction of V is in the opposite direction of the unit vector in the direction of V. You're projected going in the opposite direction, okay? And that can be seen from these here. This would be a negative number because U dot V being greater than 90 degrees. So all those are negative. And these would be positives here, here, and here, okay? Which of course then would mean this thing would be pointed in the opposite way of this, which includes that. So yeah, it does follow from all of that. Now, unfortunately, the people are not here. If they're trying to follow and I'm saying this and that, pointing here, they're not going to be able to see what I'm pointing at. It's only register projection, but just use your imagination. Okay. Now, they've got these figures in opposite order, kind of, it looks like here. But now this is saying this is basically starting off almost the same way I did. If you have some angle U, some other angle V, the projection of U onto V is going to be your U parallel. And I said at the time, the thing perpendicular to that is U perpendicular to that vector V. Okay. Now we really don't use that much because we talk about dot product and cosine. This would be dealing with the sine of that angle. So there's no real easy and smooth transition, but this also shows that the sum of U perpendicular to U parallel gives you the vector U, and that angle in between has to, just like we said before, it's the ratio of U parallel to U. You know those ratios. If you don't, but know the perpendicular, then you can get the sine of that angle, and then using its formulations go back to cosine. Not a particularly easy procedure, and I'm not even sure why you would want to, but it certainly is true. Okay. Whoops. This was the figure for example 6, I think. It looks a lot like it, doesn't it? Okay. Let's use this for example 6. Find the projection of U, which is, let me shrink this again. U is this vector here, 5, 1, negative 3, along V. V is the vector 4, 4, 2. Okay. Find the projection of U along V. okay? Based on what we just had in our last formula. This would be called U parallel V. Now, what were some of the renditions of this that would make the most sense to you? Let's go back one slide to see if we can tell. 2 slides. Okay? These I'll put down at the bottom here. Okay? Certainly this would be not that bad to do. Okay? We have V, we have UV, and VU. Okay? And we have the UV is magnitude of V squared, V, and then we have V dot V over magnitude of V squared times E to the V. Unit vector in the direction of V. Of these 3, which one do you think would be easiest to do the calculations on? I think the first one would too. The second is very similar to the first, but it looks like the first is easier. So let's go back here, and this would be, what's that rendition then? U dot V, V dot V, I can't write. Goodness gracious. Okay, V dot V times the unit, times the vector V, right? What's U dot V? What's he say? What? Huh? Okay, you're doing U dot V. 20 plus 4 minus 6, okay, over 8. Is that what you said? Oh, 16. Okay, I'm sorry, I can't hear. 16 plus 16 plus 4. Okay. What does the numerator give us? Oh, we left off one thing. I'm not going to write it out now, but it's going to be V, right? Okay. That will give you what? A little louder. Okay, that's 20 plus 4 plus or minus 6. Maybe I'm mishearing you. 18. Okay, I'm sorry. 18 over 32. No, it's not 32. 30 what? 36. Okay. Yeah, I can do that. Times V. What's 18 over 36? Is 3 over 6, right? Times V, which is? Isn't that 1/2? Is that right? 1/2 V. Okay. Now, which if you wanted to take it one more step, what would that be? 1/2 of V would be, a little louder, 221. Not a very good defense, but no, I'm just kidding. Okay. So that would be 221. All right. Got to find where that was. There it is. Yeah, 221. That is the projection of U onto V And of course, it's going to be in the direction of V. And the simplest way is U dot V, which is 18, divided by V dot V, which is 36. 18 over 36 is 1/2 of V. V happens to be 442, so half of that would be 221. Good deal. Man, leave my head. Now, we showed now that as long as V is not the zero vector, which most of the time we don't want it to be, then every vector U can be written as a sum of the projection of V parallel to U parallel to V and the vector U perpendicular to V. That is the orthogonal to V doing this. Okay. All right. This figure I pointed out before, and we're still talking about now. The vector U can be written as the component of U parallel to V plus the component of U perpendicular to V, because obviously this plus that is U. Okay? Now, how do you get this U perpendicular? Well, you could use sine of theta, okay, just like we did before, but that's not going to give us anything really all that useful. But the other thing you can do, since it's sort of inherent here, you already know what U is, you know what U parallel is, you just calculated it here, then you can get U perpendicular from U minus U parallel. Because we said that U parallel plus U perpendicular is U, right? So this would be 513 minus 3 minus 221. And what would be U perpendicular in this case? Goodness gracious, that writing is terrible. What would that be? A little louder? Not times. This is a minus sign. Subtraction.
Oh, it's a subtraction?
Yeah. 3. -1. -4. There we have it. There is your U perpendicular. For that one. Now, they weren't necessarily telling us to do it for that one, but since we had that on the board, why not do it? Okay? Now, this equation, which we have had, I've mentioned several times before, is called the decomposition of U. Decomposition of U would be, pick any vector V out there that you want. You can decompose U to be a component of U parallel to that vector V plus a component perpendicular to that vector V. So in other words, wherever you're dealing with, you can break a vector U into two components, one parallel to some given line or vector or whatever, and one perpendicular to that vector or line or whatever. In physics, we do this all the time. Two of you have had physics, right? You probably, did you have some in high school? Okay. You do this all the time, like inclined planes. Your normal force is perpendicular to the plane. The weight is straight down. You can break the weight into a component parallel to the plane and perpendicular to the plane, just like this. So it's a very common technique or practice to use, especially in physics, okay? But I'm sure there's other applications as well. The next one is going to be an inclined plane. And I think I did example 7 without realizing I was doing example 7. Let's step back to here. It says, find the decomposition of U, which is your 5, 1, negative 3, with respect to V, which is 4, 4, 2. And what we had already done was found that the U parallel was 2, 2, 1, and then that the U perpendicular was the difference between U and U parallel. And that gave you U perpendicular. Yeah, so we did it not using those terminology, that we were decomposing the vector U into a parallel and orthogonal components. So let's move on to example 8. That was the decomposition formula. So here is example 8. A very typical physics type problem. Okay? Oh. Here we have a ramp, inclined plane, whatever you want to call it. And the guy is pulling, that sort of looks like like the, what you would call those, generator or something like that up the plane. It's like he's not struggling too hard, so it's pretty light, I guess. This is the angle theta, okay? Now, here's the deal. You do this in physics a lot. You treat this object here, he's pulling on the object, the ramp is pushing up on the object, gravity's pulling down on the object, everything's operating on the object, right? Well, he's standing there holding, I don't know, maybe he's not moving. Let's just say he's not. But what we do, we treat the object as if it's a free body, and then we do a free body diagram. In other words, pick a point. I would have picked a point closer to the center of it. But who knows, maybe all the mass is down here and that's the center of mass. I don't know. But anyway, pick a point and let that represent the entire body. What are the forces acting on the body? Well, the force due to gravity is pulling downward. And I don't know why they did F. Well, I do know why. So we'll break this force due to gravity into its two components. The gravitational force perpendicular to the plane and the gravitational force parallel to the plane. Okay. Now, if this is the angle theta, okay, angle of the plane, then you know that this angle right here, because that is horizontal surface, gravity is always pulling vertically downward, so this has to be a 90-degree angle, so this makes this pi halves minus theta, okay? And that's this angle. Well, that's the same as this angle. The force parallel to the plane is parallel to the plane, so this is also 90 or pi halves minus theta, okay? And from that, you can go on and do whatever the problem asks for. Let's see what the problem asks for. What is the minimum force you must apply to pull a 20-kilogram wagon up a frictionless ramp inclined at an angle theta is equal to 15 degrees? So you want the minimum force that you have to pull on the cord here to pull it up the ramp. Well, guess what? This force, component force perpendicular to the plane, okay, orthogonal to the plane, you might say, that's completely offset by the force of the plane pushing up. That's Newton's third law, okay? An object, the force perpendicular to the plane, that's the force, the normal force they call it, of the plane pushing up on this is exactly equal to the force of, it's not quite Newton's third law.
Second law, right?
Second?
It's the second law.
Yeah, it's like the second law, except you don't have necessarily any acceleration here. So, but it's a combination of the two kind of. The force of the plane on the object is equal to the object on the plane, and that happens to be this force parallel. Okay, because that's the same force. Okay, so that's out of the picture because this force here, that force there are exactly equal. Cancel each other out basically. So the force he has to pull on the string just has it equal or slightly exceed this force here. Okay? And this force here, they told us it was a 20 kilogram wagon. So, whoops, I'm going to have to reduce this. So the mass of the wagon is equal to 20 kilograms. Is that right? Yeah. Okay. So what's the force due to gravity here? Okay. It's mass times acceleration due to gravity. That's always the force due to gravity. So that's 20 kilograms times 9.8 meters per second squared. Okay, and that would be 196 kilogram meter per second squared, which, anyone know what that unit is? You better. Huh? Newton, yeah, that's 196 newtons, which is the SI unit for force in the SI system. Unit force in SI system is the Newton. Okay. So we got force due to gravity. We know that this angle is 15 degrees. That was also given in the problem. Theta is equal to 15 degrees. So I think we know what 90 minus theta is, don't we? This angle up here would be 90 minus 15. 75 degrees. Absolutely. Okay? Now, if you know that angle 75 degrees and the cosine of the angle is equal to adjacent side, which is what we're looking for, over the hypotenuse, which was 196 newtons, then it's pretty easy to find out that F parallel, which is also this force here, the force he's going to have to pull on the string, is equal to 196, I can't write, times the cosine of 75 degrees. So if you got a calculator, pull it out and calculate. 196 times the cosine of 75 degrees. Be sure you're in degree mode. We're sort of going back and forth between degrees and radians. Always make sure of your mode first. What does this come out to be? 50.7 newtons. Okay, let's see what they got. They just rounded to 51. Okay, it's approximately 51 newtons. Now, I was trying, yeah, I think that makes sense, because here they gave this to two significant digits. You might argue that's two significant digits. We don't know for sure with the zero, but we'll count that. So we'll round that to 51. Make sense? So since gravity pulls the wagon down the ramp with a 51 Newton force, it takes a minimum of 51 newtons to pull it up the ramp. Anything more than that, and you're accelerating it up the ramp. In other words, it's picking up speed. Not necessarily here. All right, graphical insight. Okay? it seems that we're using the term components in two ways. I didn't know we were, but let's see. We say that a vector U has components AB, okay? On the other hand, U dot E is called the component of U along the direction of the unit vector E. Okay, now I see what they're talking about. Okay. If you're saying U is equal to AB, let me blow this up. I don't think I'll be writing on it. Okay? Yeah. If this is U in the XY plane, then it has component A units in the X direction, B units in the Y direction, J direction. So its components are AB. But that same vector, if it happened to be traveling up a plane here, and that plane was not in the direction of the X vector, E, then it has a component parallel to this vector E, the unit vector E, and one perpendicular to the unit vector E. So it has a component parallel and perpendicular. Same thing here, parallel to the x-axis or perpendicular to the x-axis. Just depends on what axis you're talking about. So this is just the ijk, if you had a third dimension here. So that'd be A times I. This would be the dot product of U times this vector E in the direction of E. Okay. So, and then they drew, and by the way, E and F here, I guess it looks like that's the same. Something to me makes that length a little shorter than that, but maybe it's not. And those are the unit vectors along the plane and perpendicular to the plane. Well then, of course, according to a different axis, the same vector will have different components. This component here, that component there. Okay. I guess that's the conceptual insight. Okay, let's rehash a couple of important facts we've hit. The dot product of a vector with itself is, as long as this vector is not the zero vector, it's a positive number. It's the maximum projection of V on itself, you know, it's the whole vector, okay? It's its magnitude squared, okay? Well, that's not what I want. Okay. One definition of the dot product is this one. V dot W is magnitude of V times magnitude of W times the cosine of the angle in between. Of course, the other is just V1 W1 plus V2 W2 plus V2 3 WV3. It's another definition of a dot product. They didn't give a slide of that. Okay? When you have two vectors U and V and you're wanting to project U onto V, you have a component of the vector in the direction of V, that's called U parallel, and then you have a second component perpendicular to that vector, U parallel. And if you want to refer to that not to vector V, but to the unit vector in the direction of V, then you take V divided by its magnitude to get that unit vector. All right, this leads to some other renditions of that same expression, U parallel. Now they do one that is this was the old edition. In the new edition, we have the 3 equivalent, this being one of the 3. I forgot, I can't write on this. So let's write on it now. This being one of the 3, another being U dot V over magnitude of V squared, because that's what V dot V is, times the vector V, which then we could split that into U dot V over magnitude of V times E sub V, because V over E sub over magnitude of V would be E sub V. And then this over itself would then be U dot E sub V. Sorry, I usually put hat over unit vector times E sub V. And that's what this one is. Okay. So there's several ways you can express those. Okay. And then the component of V, of U along V, is U dot V they've left some stuff out there, it looks like. Okay. This is similar to what they had, but this is a component which is not a vector. The component, the magnitude of that along V would then be, from the previous slide, I can't write here, sorry, I keep forgetting. U dot V over magnitude of V, okay? Because that's what's multiplied by the other. And this is your magnitude of U times the cosine of theta. Okay. Which is basically takes us right back to where we began, that U, V, magnitude of U times magnitude of V is times the cosine of theta, and you can back everything off from there to get back to the same form. So nothing too new there. And I'm afraid we are out of time. Sorry about that. We didn't have a chance to go over the preliminary questions. You want to lead off with them next time, or y'all do them at home? And if you have any problems with them, ask about them next time. We'll just start at 12:4. Which way you'd like to go? Lead off with them, or you do them at home? Lead off with them. So we'll start with this next time. We won't need the slides for 12.3, but we will start with that. Then we'll move on to 12.4, which is cross products. Similar but different, okay? A different kind of multiplication of vectors. And after that, we will talk about planes in free space, not just vectors in free space, but planes in free space. It's a fairly short section. Survey, and then survey of quadratic surfaces. I guess we'll count that in this one. In the past, this is where I've begun to teach, but we weren't there to begin with. So what we'll probably do is have the second test just through 12.5, and then the third test will be from 12.6 into 13. All right, we'll go from there. We'll close this off.